So hello everyone, I'm NAVID, ESR6 in the FLOAWER project, and today I'm going to present a portion of my result out of my PhD. It's a pretty long title, Experimental Tank Test Analysis of Floating Wind Turbine Model using Underwater Particle Image Velocimetry. But for this instance, the running title could be a framework for quantification of floating wind viscous drag. And I'm going to elaborate on this idea through the set of the slides. The first question is that what is a viscous drag? So viscous drag simply is the drag force experienced by the moving structure in a fluid medium. And this is because of the viscosity of the fluid. Why it is important in context of floating wind turbine? Because currently engineering software use potential theory with combination of the Morrison equation, and this could lead to have some error in terms of the hydrodynamic response up to 20%. The main result of and the main uncertainty to create this error is the uncertainty in calculation of hydrodynamic quadrant damping. And one effective parameter in estimation of this damping force is the correct choice or valid choice of the drag coefficient. So if we're going to look through this, if we have a realistic estimation of the hydrodynamic drag, we could have a more realistic estimation of the quadratic damping, and then our potential theory method would have a better response. One of the current widely used approach is to use CFD to calculate the viscous drag, integrate it into potential theory, and have a better response instead of using the Morrison equation itself. But the problem with the CFD model is that it demands for significant computational resource when you consider multi-degrees of freedom, coupling with turbines loading, and testing varying range of mid-ocean condition. So to date, there is no guideline or trade-off introduced in the literature to mention how much the level of dynamic complexity for this CFD solution should be when you want to only integrate the drag result with the potential theory. You're not going to go to analyze all the platform by the CFD only, you just want to calculate the drag terms. So in this research, I'm going to just present a guideline, a trade-off between the dynamic complexity and its effect on a viscous drag calculation. And what I have done in part one was to do a tank testing with the help of underwater particle image velocimetry. I'm just going to elaborate the test setup really quick. So we had two underwater camera, one laser guide arm, which through a set of mirror guided the laser light to the underwater area. We have a laser optics here, which create a light sheet when the laser pass through. We have some hollow glass particles for the purpose of the tracing the flow, and the system working at 20 hertz. So the method is SPIB method. The platform is NREL MIT platform with a 1:8 scale ratio, and we consider 3 test configuration. So what you can see here is the full system configuration where the platform is free to float. It's moored, of course, and we have the turbine loading. We also, in terms of the dynamic complexity, we also have 2 other configurations. The second configuration is to have a floating platform, but the turbine is not working. It just presented. And the third configuration is the fixed platform. So we had some horizontal pipe above the water level area just to keep the platform stationary. And what we're going to do is to investigate this field of view for these 3 configurations in a varying range of the wave heights and wave periods. So the first result that we have found was the velocity contours behind the floater. So you should consider the floater here. And this is the area behind the floater. The first row shows the velocity vectors in x direction. The second row shows the velocity vectors in cross-flow direction, v direction. And here we have the fixed model, floating model, and the full system. If we look through this configuration, this result, we can see that there is present of some lee side vegs are present. You just need to consider that as a circulation zone. we have them in 3 configurations. So the behavior is not changed when you increase the dynamic complexity. But the point is, when you move from the fixed model to a floating model, or in other words, when you introduce the degrees of freedom, this relocation, these circulation zones relocate to the far side of the platform. Looks like the motion of the platform pushed them like further away towards the beach. And their S-turns also increases by almost 20%. And when we introduce the turbine loadings, we see an opposite effect. So basically, the turbine loading somehow dampen out the motion of the floater, and the ingenerated eddies by the floater motion, or their share, would be reduced. So as you can see between the contours, the S-turns of the eddies has decreased by almost 11%. So it's reduced. But if we want to have a clear picture, we need to look through the turbulence kinetic energy and, of course, the turbulence intensity. So when we compare the fixed, floating, and full system, we can see that between the fixed and floating configuration, when we introduce the degrees of freedom, the TKE value increased by almost 102% in spatial manners, and 95% in terms of energy level. And when we introduce the turbine loadings, so now we're going to compare these two results. It's reduced by 35% in terms of spatial and 26% in terms of the energy level. And the result of the turbulence intensity are in the same range. So what we can see from here is that if you model a full system with a floating one, you're going to have an overestimated result. But they are pretty similar to each other. But when you want to model a full system with a fixed model, you're going to have really underestimated and out-of-range results in terms of the viscous drag. But if we want to quantify it better, and if we want to have this number more valuable for the title, we can look through the Reynolds stress tensor. So on the top right side, you can see the diagonals value of the Reynolds stress tensor. On the down left side, you can see the off diagonal. So what you can see here, the red line is for the fixed model. The black line is for the full system, and the blue line is for the floating one. So in terms of the similarity for the pressure presented arrays and for shear presented arrays, we can see that turbulence stress are increased when you move from fixed model to the floating model, and decrease when you move from floating model to full system. But how much is the similarity? So basically, the similarity between the full system and floating one is in the range of 62 to 76% in terms of the Reynolds stress tensor. And for the fixed and full system, we have something like a range of 44 to 57. So basically, we have an error range of 54% for the fixed and full system, and almost 30% between the floating and full system. So this is the result for one wave case. So if we want to see the effect of, or the sensitivity of the result towards the change in wave height and wave period, we can look through this result. So basically what we have done here, in this set of results, I had the wave period fixed and the wave height changed. And in this set of results, we have the wave height fixed and wave period changing. So what we can see, in all scenarios, the correlation between the floating and the full system is far more compared to fixed and full system. And when you increase the wave height and the wave period, this correlation falls down because you introduce more turbulence to the more incoming turbulence. And the results are more sensitive to wave height change compared to wave period change. And this could be because when you increase the wave period, you somehow tweak the wavelengths as well. So basically, platform has more time to being introduced to incoming turbulence of the water medium itself, not the motion of the platform. well, if you want to conclude all the results that I've presented to you, so we can say that modeling the full system with only a floating model could result to error band of at least 30% in terms of the viscous drag estimation. While modeling it with a fixed model will lead to error band of 54%. But this is all for the condition that tested. We need to have more floater tested, more different wave heights and different capacity for the turbine. And as the wave height and period increase, the similarity between the all scenarios will decrease further. This was the result of the part 1. I've also have the part 2, but here we can consider it as a future work. So what I'm going to do here, or what I've already done over there, was to analyze all the configuration in a CFD software to see what else parameters could have contribution into the uncertainty of the viscous drag estimation. So thank you so much. If you have any question, I would be more than happy to answer.
Thank you, Navid. So are there any questions in the room? Yes.
Yeah, I've at least one question, maybe two. The question about is about you have a fixed, a floating, and a complete system.
Complete system.
Is there the motion? Is it a fixed motion you give to the floating and the fixed system, or is it, or is, for instance, is fixed? The motion of the cylinder is 0, but and then you have your floating. It has a certain velocity,
Yeah.
And also if it's a full system, it has a certain velocity. And is it for the floating and the complete system? Is it the same?
Yes, so in all 3 configurations, we have one TLP platform. But the difference between the configuration is the amount of degrees of freedom and the turbine's loading. So for example, for the fix, we just had some pipes that the platform is attached to it, so it's not moving at all. It's like a fixed model in a numerical software. But here in a tank test, so it just fixed, it's not moving. Only the water and the wave, we have only the incident wave. For the floating, we removed those bars. The platform is moved, but we did not turn on the turbines. And for the full system, it's the same as floating, but we had the turbine loading as well. That was the difference between 3 configurations.
Is it also, the rotor is also turning, the wind turbine is operating?
Yes, for the full system, the rotors is also turning. Yes.
But then you, I have the impression that you want to know the viscous damping caused by the hydrodynamics.
Yeah.
But if you have a wind turbine running on it, it's known that the aerodynamic damping of a wind turbine is very large. So you are now mixing, for the full system, you are mixing aerodynamic damping for the wind turbine if it's rotating together with hydrodynamic damping.
Yeah, that's correct. That's why we have the floating configuration in the middle, where the turbine is turned off. You know what I'm trying to say? So
I understand what you are saying, but I'm also trying to, maybe that's more for, I started as an engineer in an engineering company doing for this kind of calculations with potential flow, and then you have to estimate also a viscous drag.
Yeah.
So, and I'm also wondering, okay, you do your research, and I understand why you are doing and why you are looking at it, but that at the end, I think as a user of FAST or a computer, you want to have some CD value in your for your Morrison equation, and that translation I don't see at the moment. That's one thing, and also. When I was an engineer, or when you look in hydrodynamic textbooks on where you have cylinders, like Faltenson offshore mechanics, you have this. There is a dependency on the one hand, you can have a fixed cylinder, and then with a flow, but you can also have this movement. And then you get into this Carpenter numbers where you have this amplitude of your movement, and that has an effect on your CD value.
CD value.
So, and that's where I wanted to find a link between what I'm used to and what you are doing, and that's also my question. Do you have, is this motion, is it the same for the full system and for the only floating one?
Yeah, that's a really good question. Thank you for asking. So for the part one that you've mentioned about the software, well, the point is that those software has an error range. So if we want to have better estimation, we need some people producing some high quality, high fidelity validation data. So the numerical developer could use this data for creating better codes or for tweaking better codes or introducing better drag values for the context of floating offshore wind turbines. And for part two of your question in relation to the what is already available in the textbook, that's actually correct. So basically, if you want to consider a fixed cylinder or even a moving cylinder in an incoming one medium fluid flow with a constant velocity or even with an introduced turbulence, there's plenty of literature on it. But if you want to consider and if you want to analyze a floating offshore wind turbine with an incoming wave and to see what's going to be the similarity or difference in terms of the flow in comparison to those literature, well, there's nothing available that much in those areas. So that's why this research could act as a patch, and it could be like find a relation into that manner.
Okay.
Thank you. Another questions? Yes.
Thank you very much for your presentation. I found it very nice, and I was first wondering about your interpretation to the fact that when you have aerodynamic, that you account for aerodynamic, why you have less energy in the wake of the platform. Is it like some kind of that the turbine extracts some of the energy of the waves, so that in the end you have less energy in the wake of the platform, or what's your interpretation on that?
Well, that's actually a really good question. So basically the platform that I've used is a TLP, which is surge dominant, and I had a truss emulator at the top of it. I can guess that there might be a relation between the type of the platform that we're using here. If we change it to a semi-submersible, which is going to be a pitch dominant a little bit, maybe the result of the turbine's effect show them in another manner, show themselves in another manner. So I think more platform needs to be studied to have like a general hypothesis. But for this condition that I've tested and this type of the platform, the result was like this one.
Okay, and also regarding this field, can you, with this data, go back to the viscous load that has the viscous drag that you were mentioning at the beginning? Can you estimate them with this wake field or not?
Well, with this contour field we cannot, but the nearest parameter that we can talk about is the Reynolds stress tensor. But we also have other parameters as well. So that's why in part two, I've used the CFD, and I'm going to use the load cell data and the tension in the tethers into that paper. So that's where those data comes with the combination. So the CFD will tell you a part of the story, the PIV will tell you the other part of the story, and then when you have them all together, you can see what's going on behind the floater.
You expect to somehow validate your CFD framework with this data, and then with the CFD simulation have access on what's happening on the floater itself.
Yes.
So it's like kind of a dual approach.
Yes, and
it's nice.
And as well, we had some accelerometer at the top of the floater. We had some load cell that's been used. We have some current profiler and acoustic velocimetry measure system. So those data are also available. Those data are going to tell another story as well. So all the data should be validated towards each other, and then we can have a general hypothesis.
Okay, thank you. Nice.
Thank you.
Thank you. So I have also a question related to the thrust actuator. Which type of inputs did you put it in this thrust actuator? Was it constant thrust? What is constant thrust coefficient, or did you apply something more realistic?
Well, that's a really good question. So I'm going to show it on the photos. The problem that we have here is about the health and safety requirements. So we had a really wide and large tank hole area, so we couldn't use the laser with a naked eyes. What we have did was to put a laser safety cover over the area of the measurement. So that way the laser would not make somebody blind. But the point was, when we put this cover, we couldn't have the Qualisys cameras to capture the movement in the PIV measurement state, so we couldn't use software in the loop or something like that. The feasible option was to use a thrust emulator with a fixed thrust value, which is calibrated based on the rated drag force into the real prototype.
Mm-hmm. And maybe another question regarding to the PAV setup. How many pair of images you were using to do your statistics?
Yes, so the acquisition rate was 20 hertz, and I had 10 minutes of data. So it was like 20 hertz in 10 minutes was almost 8,000 to 10,000. But the first initial set of data are not valid, so 50 or 100 first set of data should be just deleted without looking into them. It was in the range of 9,000 to 10,000.
Okay, so it's quite a high values of images that are used to make the average. Because I found that the Reynolds stress tensor images were still quite scattered. And so I was expecting with, I don't know, 10,000 images or something like that you would have something which is smoother.
Smoother. Yeah, well, the point about the Reynolds tensor here, or even about the TKE and TI, is that we have an irregular incoming wave. And this is the time average of the result of the irregular waves. If it was regular, it would be more neat and more like...
Okay. Are there any other questions in the room? We still have a bit of time. Yes, Martin.
Just related with what Sandrine said, so maybe the PIV window is too small for your data, or did you try to play with these parameters?
Yes, true. So the PIV window is, the maximum window was about 30 to 30 centimeter, but we've of course lost a bit of the corners because we need to align it based on the calibration plate.
But I mean the windowing for the correlations when you run the PIV algorithm? The interrogation window.
Interrogation. Yes. So you mean the field of view here? This field of view.
So that, in the post-processing, you will divide it in small interrogation windows that tend to be 16 to 32 square pixels?
Oh, you mean about the post-processing. So the post-processing was based on the ITTC. I remember that I've used a post-processing method based on the cross-correlation with decreasing window size. The initial window size was 64 to 64 for the first pass, and the final pass was 32 in 32 with 50% overlap in both X and Y direction.
Okay.
And a Gaussian fit was used in the post-processing method.
Okay, thank you.
No problem.
One last question? No? Okay, so let's sound
Thank you so much.
NAVID again.